So today we will be doing the Bohr's model of atom. So let's start with the first slide. So let's study about firstly emission and absorption spectra. Emission spectra is nothing but when there is a substance, for example, and it absorbs some sort of energy. Okay, it will be excited. Okay, then what will happen? Excited states are not stable. It will radiate the energy. That means it will give off the energy. Now, when this energy is given off, the spectra corresponding to it is emission spectra because it is emitting the energy. Okay, and absorption spectra, it is just the opposite of it when the substance is absorbing. Like look at the third point that I have written. It says absorption spectra is the photographic negative of our emission spectra. Like in case we have obtained the emission spectra, which is what, as I told, that a substance will be there, it will absorb the energy, get excited states are not stable, so it will get de-excited and will radiate the energy, or better I should say emit the energy. This spectra corresponding to this emission of the energy is emission spectra, and the photographic negative of the emission spectra is absorption spectra. Look at these images. The first one is the emission spectra, where you can see some bright lines over the black region. These bright lines are actually the those emitted radiations. These are actually corresponding to those emitted radiation when the substance comes from the excited state to the lower ground state. Okay, and the opposite negative, okay, the photographic negative of this is given in the second image, which is the absorption spectra, where you can see that the black regions in the emission spectra are replaced by the colored regions in the absorption spectra, and the bright lines are uh, replaced by the black lines. Okay, so they are both just opposite to each other. You should only know what they are and their representations. The actual spectra that you will study will be in the higher classes. So let's move on to the next topic. Okay, so first let us learn about line spectra of hydrogen. Now, what happens is that electric discharge is passed through the gaseous hydrogen, and the hydrogen single bond, it breaks down, and the hydrogen molecule again breaks down to the hydrogen atom, which are excited. Now, since they're excited, they have high energy and they want low energy, so they need to come back to some lower levels. Now when this happens, there occur the lines. These lines in the hydrogen spectra, okay, these lines are of discrete frequency. Now by discrete frequency, I also explained word discrete in my previous videos, which means the value of the frequency will be quantized. Okay, and why is that quantized? Because of this formula, it will be the multiple of RH. Okay, so the value of the frequency is quantized. Now let us focus on the formula. So this is the formula of wave number, which is equals to 109677 in the bracket 1 by n1 square minus 1 by n2 square. Now when they're coming from a particular level to a lower level, for example, in question or numerical, you are given with two values of n, 3, 2, or maybe 4 and 5. Now what you have to do is, in place of n1, no matter how the or like how the your atom is coming back to the level, or which level we are talking about, every time you have to keep the value of n the lower one. N1 is lower value and n2 is higher value. Why? Because if that will happen, now n1 it will be lower value, then 1 by n1 square will be greater than 1 by n2 square, and this whole term will be positive, which in turn gives the positive value for your wave number, your frequency, your wavelength. And all these quantities are positive, they are not negative. Okay, so that is why we are keeping your n1 always shorter than n or smaller than n2. Okay, now what happened? So I think you understood the formula. I will repeat it again. First, I want to talk about these lines. Actually, these lines were discovered by different scientists, and they were later on named after them only, like Lyman, Balmer, Paschen, Brackett, Puffin. We will be discussing it in the next slide. Okay, now let's coming back to the formula. So here I'm repeating, n1 is smaller than n2. Why? Because if it will be smaller, then only your positive value for wave number will come. And further we can calculate frequency and wavelength also, and they are also always positive. So your n1 should be smaller than n2. This is simple maths and you should know this. So I wanted to explain that your hydrogen atom is the only atom which have a very simple spectra. Spectra for other species is very complex. Now look at this diagram. When from any higher level, your atom is coming back to a ground level and your n is equals to 1, then it is called Lyman series. When your n is equals to 2, it is Balmer series. When your n is equals to 3, it is Paschen series. For 4 it is Brackett, and for 5 it is Puffin. Okay, your n2 can have any value, 2, 3, 4, 5, 6, 7, 8, depending on your type of series. Now, one thing that you have to learn is that your Lyman series lies in the ultraviolet region, your Balmer series lies in the visible region, and the other three series lies in the infrared, or I should say, infrared region. Okay, so you should know how to draw this diagram, and you should know from this table that which series lies in which spectral region. That's enough for the hydrogen line spectra to you. And now we will be moving to the Bohr model of atom. Okay, you have to learn. Okay, now you have to learn these things. Okay. Okay, so the most awaited topic, for which we studied so many topics. Okay, so that's the Bohr model of atom. Now, what Bohrji said, that your electron actually moves around the nucleus in a circular, or I should say concentric orbit. Okay, these orbits are actually called stationary states or stationary energy levels. Now, why are they called stationary energy levels? uh, like, by word stationary, this statement is from Pradeep's, that by word stationary, we don't mean that the electrons are stationary in these orbits. Electrons are always moving around the nucleus, but the word stationary here means that the energy of these energy levels is quantized. Okay, electron can't move around nucleus in any orbit. There is a fixed value of energy which will make it suitable for electron to move around the nucleus. Okay, electrons can get excited to some levels, they can get de-excited to some other level, but all these levels will have some particular value of energy which is quantized. And by quantized, I mean that they are some integral multiple of a particular value, which we will be studying in further slides. Okay, so this is what Bohr said. And one more thing he said is that they do not radiate energy while doing so. Like, there was this limitation of the Rutherford model of atom, right? So it was removed here. Bohr ने ऐसा बोला that they do not radiate energy and they will not fall into the nucleus, and hence their atom is stable. The second point also says the same thing, I guess. The electron will move from a lower stationary state to a higher state when required amount of energy is absorbed by the electron. When electron moves from higher state to lower. Okay, so it says that uh, you need a particular amount of energy in order to go from higher state to lower state, or lower to, or you need from lower to higher state, and you need to radiate a particular amount of energy in order to go from higher to lower state. So all this says that your the energy levels, or the orbits in which your electrons are revolving around the nucleus, are of some particular energy. They are of not some random energy. They have a particular energy, and that energy is quantized. It has a fixed value. Now, Bohr calculated the values of the frequencies, energies, or angular momentum for these orbits, okay, or for the electrons in these orbits, and he gave some formulas. He did a lot of calculations. These calculations are there in higher studies and higher books if you decide to go for, but for now you just have to learn the formulas. For frequency of radiation absorbed or emitted when transition occurs between two states, the formula is mu is equals to del E upon H, which is equals to E2 minus E1 upon H. Okay, so this is the formula. The formula actually is incomplete because right now you don't know the formula about energy, so we will be looking the energy formula also, and from that you will be calculating the frequencies. Okay, so just remember that you have to just like we know that E is equals to H mu. Okay, so mu will be equals to E upon H. Now for mu upon H, now your energy, sorry, mu will be equal to energy upon H. Okay, so your energy difference is required, right, between the two levels in order to calculate the frequency of that electron or that particular line of the spectra. So this is the formula used. Also, the angular momentum formula, your mbr is equals to nh upon 2 pi. So angular momentum is also quantized, look, because it is your multiple of integral multiple of h upon 2 pi. Your n is having value 1 2 3 up till infinity, right? So it says that angular momentum of an electron in a given stationary state can be expressed by this following equation, and it is quantized. It is having a fixed value. It again doesn't have any random value, and this is the formula for the calculation. Your m is your mass of electron, v is the velocity, r is the radius of the orbit, and nh upon 2 pi, h is the Planck's constant, and 2 pi you know that, and n is the orbit number like 1 2 3 4 5 6. Okay, now we will be calculating the formulas for radius also. Okay, so that's in the next slide. Let's move there. Now, very important point, the stationary state for electron are numbered as 1 2 3. Now let us imagine one thing. For example, your sun is there. Okay, take it as your nucleus. The first orbit is of Mercury. Now that orbit is n is equals to 1. That is your stationary orbit. First stationary orbit, your ground state. Second is of Venus, right? It's Venus, right? So that is your n is equals to 2. Third is your n is equals to 3. That is of Earth, and so on. Okay, so these are the stationary states around the nucleus for where electrons can, for example, your Mercury is at n is equals to 1. Now Mercury wants to go to the orbit of Earth, so it is the second excited state. For n is equals to 1, it is the ground state for Mercury. When it goes to the Venus, it is going from 1 to 2. That is, Venus ka orbit is its first excited state, and the अर्थ का ऑर्बिट n is equals to 3 is its second excited state. So सबसे पहले क्या आया, ground state, first excited state, second excited state, then third excited state, and so on. And these n is equals to 1 2 3 are known as principal quantum numbers. Now as we saw, the we got the picture of the orbits, like how they are around the nucleus. Now since they are orbits, they are concentric, they should have some radius. Okay, so your radius expression is n square a naught. Now what does this expression suggest? That your radius is also quantized. It is having fixed values. It can't have any random value but a fixed value based on this formula. The radius is integral multiple of your a naught, where a naught is equals to 52.9 picometer. Picometer is 10 to the power minus 12 meter. Okay, सो फॉर एग्जांपल n इज इक्वल्स टू 1 वाला ऑर्बिट है आपका मरकरी का ऑर्बिट, फॉर इफ वी टेक इट इन दैट पिक्चर वाला सेंस, तो उसका ऑर्बिट का रेडियस कितना है, दैट इज योर 52.9 पिकोमीटर, बिकॉज n is equals to 1 and 1 का स्क्वायर is 1. Okay, so In this manner you can calculate the radius, and you need not to learn the value of radius for each and every orbit. Okay, it will, you can calculate it from this formula. Now till now what we did, your angular momentum is quantized, your radius is quantized. Now we will see that your energy is also quantized. How? Look at this formula. What does this formula say? That is, energy of a n orbital is equals to minus RH 1 upon n square, where your RH ka value, your RH is again Rydberg constant, but this time the value is not 109677 centimeter inverse. The value is your 2.18 into 10 to the power minus 18 joules, because we are taking unit as joules. Okay, so your energy is also quantized. Look, minus RH, and it is the integral multiple of this Rydberg constant. Keep value of n as equals to 1, 2, 3, 4, 5, 6, 7, 8, and you can calculate the value of your energy of that particular orbital. And you need not to again learn the energy of any orbital. You can just calculate it from this formula. Okay, so हमने क्या क्या क्वांटाइज किया? एंगुलर मोमेंटम इज क्वांटाइज्ड, योर रेडियस इज क्वांटाइज्ड, योर एनर्जी इज क्वांटाइज्ड. नाउ सिंस you know how to calculate energy, let's calculate the energy for the second orbital. For the second orbital, minus 2.18 into 10 to the power minus 18 into 1 upon 2 का square, that is into 1 upon 4. तो आपका वैल्यू आ जाएगा माइनस 0.545 इंटू 10 to the power minus 18 का joules. So this is how we do our things in Bohr model of atom. Now, if you paid attention, you would have seen that there was a negative sign in the expression of energy. Why was it there? Like energy, why can't energy be positive? Your energy is always negative. Why? So this is actually a funda, and you need to read this line because for that. When the electron is free from the influence of nucleus, energy is taken as zero. Electron in this situation is associated with the stationary state of principal quantum number is equals to n is equals to infinity, and is called as ionized hydrogen atom. Now when the electron is attracted by the nucleus and is present in orbit n, energy is emitted and its energy is lowered. Now what happens that when your electron is free from the influence of nucleus, like it is so far from the nucleus that there is no effect or no attraction from the nucleus towards the electron, that particular orbital is called n is equals to infinity, and at that stage the energy is zero. Now when the attraction will be there, your this what should I say, your electron will come towards the nucleus. It will be feeling some attraction and will be coming to the lower levels, and this can only happen if it radiates or gives off the energy. Now already the energy was zero, अब वो उसमें से भी अगर दे रहा है, so the energy comes to be negative. Okay, so this is why the energy is negative. Now what happens that you can also calculate for these energies, radius, angular momentum, etc., for not only hydrogen atom but hydrogen like atom too. Now, what are these hydrogen like atom? They have one electron, but they are different species. Now, how is it possible? So, I have given some examples: helium plus, lithium 2 plus, and beryllium 3 plus. Now, helium in itself is having two electrons. Now helium plus means one electron is lost, so one electron is remaining, and one electron is hydrogen. Okay, so helium plus species is hydrogen like atom. Similarly, beryllium 2 plus, 3 plus, and lithium 2 plus are there. So you don't have to do anything. You just have to make a particular change in the formulas. For energy, you have to multiply it with z square, and for radius, you have to divide it by z. Just this is the thing that you have to do. Otherwise every all both the expressions are same, and that's how we calculate energy and radii for uh, species which are hydrogen like but are not hydrogen atom. And these species are your helium plus, lithium 2 plus, and beryllium 3 plus. Now, I just wanted to discuss some formulas. Now, what we did earlier was we just calculated the wave number when your electron is moving from some particular level to some other level, okay? But in that case, we were just seeing the line spectra of hydrogen, okay? So the electrons were coming from the higher level to the lower level. Now what can happen that your electron can absorb energy, it can go to some higher level, it can, or the electron can radiate energy, and it can go to some lower level. So you just need to calculate your energy and frequency in that cases. How will you do that? Your energy difference between those stationary levels in which your electron transitions are taking place will be E final minus E initial. So E final is of that orbit जिसमें वो जा रहा है, एंड ई इनिशियल इज दैट ऑर्बिट जिसमें से जा रहा है, एंड योर डेल ई विल बी इक्वल टू आर एच ब्रैकेट में 1 अपॉन एन आई स्क्वायर माइनस 1/nf स्क्वायर. ओके, यू नीड टू लर्न दीज फॉर्मूलाज. और ये फॉर्मूला आया कैसे? फॉर एग्जाम्पल दीज आर फॉर हाइड्रोजन. एनी वन लाइक कैसे आया ये फॉर्मूला? लुक, ई एफ की करस्पॉन्डिंग एनर्जी क्या होगी? It will be RH upon NF square. ओके, माइनस और ई वन की सॉरी माइनस का आर एच अपॉन एन एफ स्क्वायर, एंड ई आई की करस्पॉन्डिंग होगी माइनस का आर एच अपॉन एन आई स्क्वायर. हमने अभी पीछे पढ़ा एनर्जी का एक्सप्रेशन, राइट? इट इज़ माइनस आर एच अपॉन एन स्क्वायर. तो अब ई एफ की नेगेटिव हो गई और माइनस ई आई की भी माइनस आर एच अपॉन एन स्क्वायर, तो नेगेटिव नेगेटिव पॉजिटिव हो जाएगा. तो अब ई आई वाला पार्ट पॉजिटिव, ई आई और नेगेटिव साइन वाला पार्ट इस पॉजिटिव हो गया, तो वो हम पहले लिख लेंगे, और ई एफ वाला पार्ट नेगेटिव हो गया तो उसको हम बाद में लिख लेंगे. और उस तरीके से ये फॉर्मूला डिराइव हुआ है. डेल ई इज इक्वल्स टू आर एच 1/ni² माइनस 1/nf². और आर एच का वैल्यू वी नो दैट. ओके, और इसी तरीके से वी कैन कैलकुलेट फ्रीक्वेंसी ऑल्सो. नाउ डेल ई इज इक्वल्स टू एच म्यू. ठीक है, तो आपके पास डेल ई का वैल्यू आ गया, तो उसको एच से डिवाइड कर दो बस. तो आपका क्या आ जाएगा? म्यू फ्रीक्वेंसी आ जाएगी. बस यही था, कुछ भी नहीं था. आपको कुछ नहीं करना है, आपको बस ये फॉर्मूला याद रखना है. जब भी आपका इलेक्ट्रॉनिक ट्रांजिशन हो रहा है किसी ऊपर वाले लेवल से नीचे या नीचे वाले लेवल से ऊपर, तो आपका फॉर्मूला होगा एनर्जी डिफरेंस विल बी ई फाइनल माइनस ई इनिशियल. ठीक है, इस पार्ट को याद रख लो. सेकंड वाला फॉर्मूला आप खुद डिराइव कर लोगे. कैसे? आपका एनर्जी का एक्सप्रेशन होता है माइनस आर एच अपॉन एन स्क्वायर, तो ई फाइनल के करस्पॉन्डिंग होगी माइनस आर एच अपॉन एन एफ स्क्वायर. फिर माइनस का साइन आएगा, अब ब्रैकेट में लिखना ई आई के करस्पॉन्डिंग होगी माइनस का आर एच अपॉन एन आई स्क्वायर. अब माइनस माइनस प्लस हो जाएगा ई आई के केस में, तो वो प्लस वाले को हम पहले लिख लेंगे. that will become RH upon expression will become RH upon NI square माइनस का RH upon NF square. RH हमने कॉमन ले लिया, ब्रैकेट में 1/ni² माइनस 1/nf². RH का वैल्यू जूल्स में हमको पता है, एंड this is the expression which helps us to calculate our things. Now let us move to the next slide. Here we have a numerical, a very easy one, but उससे पहले let us see the limitations. Limitation कुछ नहीं थी, ये हमें ये नहीं बता पाता था, like it couldn't explain the ability of atoms to form molecules, and it also failed to account for the fine lines. Spectra में actually fine lines भी आती हैं, there are doublet. Okay, so you will study these things in higher classes, so don't focus on those things, just learn that. And let us now look at the problem. तो कुछ भी नहीं है. कैलकुलेट एनर्जी एसोसिएटेड विद द फर्स्ट ऑर्बिट ऑफ हीलियम प्लस एटम. तो एनर्जी का एक्सप्रेशन आपको पता है, एंड इट इज हीलियम लाइक एटम, तो जेड स्क्वायर से हमने मल्टीप्लाई कर दिया. यू जस्ट हैव टू पुट द वैल्यूज. योर जेड इज atomic number, A was atomic mass, right? Z is atomic number, so Z is equals to 2, and associated with the first orbit बोला गया है, so n is equals to 1. Just put the value, you will calculate it. Also they have asked us to calculate the radius, so radius का formula भी आपको पता है. You just have to put the value of n and z, you will calculate your things. Now It depends on you whether you have to put your values in nanometer, angstrom or picometer. जिसमें रखना है रखो, nothing will be wrong. Okay, so this is the end of the video. Wish you all the best and have a happy learning, and we will be posting other topics too soon.